All right, in this next video, we're going to be looking at permutations, which count things where the order matters and repeats are not allowed. So this is similar to the last situation in the last video where we did order matters and repeats were allowed. We're changing one thing that repeats are not allowed. So let's do a similar situation to last one when we're thinking about a slate of officers. So suppose there's an organization with just 5 members. The organization wants to select a slate of 3 officers, a president, vice president, secretary. There will be a single individual chosen for each office, so no co-officers. A person is not allowed to hold more than one office, so there's no repeats here. How many different slates of officers are possible? Hint, let's go ahead and draw out a probability this time. Probability tree this time. I made it small enough where we can do that. Go ahead and work it out yourself. Press pause now. Well, hopefully this is what you came up with. Let's say we choose our president first. There's 5 people to choose from. So there's these 5 dots here represent the 5 choices for president. But once we pick person A here, then we could pick person B, C, D, and E, but we can't pick person A for the vice president. So these are here. And for example, if this is person B, we could pick person A, C, D, and E, but not B. So if you notice, we have in each case we eliminate one of the choices, so we're down to 4 choices for vice president for every 1 choice for president. Once we pick that, then we've eliminated 2 people. So like here, we've eliminated person A and B. Then it's either C, D, or E for the next person. And similarly for all the others. So 5 choices for president. For every one of those, there are 4 choices for vice president. And for every one of those, there are 3 choices for secretary. And so we end up multiplying these together 5 times 4 times 3, which is 60 different slates of officers. Okay? Let's have you do another one. This one's going to be a little bit bigger. This time we have 25 members, and we're going to select a slate of 4 officers: president, vice president, secretary, and treasurer. Again, there will be a single individual chosen for each office. A person is not allowed to hold more than 1 office. How many different slates of offices are possible? Again, this time let's think about a probability tree, but don't actually draw it all out this time. Just think about it and use it to help you with your computation. I bet you can do this one yourselves. Press pause now. Work it out. Okay, well, if you think about your tree, we have not just 5 this time, but 25 choices for president. But once the president is picked, we're down to only 24 choices for vice president. And once those 2 are picked, 23 for secretary, and for each of those, only 22 then for treasurer. So when you think about the way your tree is going to be set up, the number of total paths through the tree will be 25 times 24 times 23 times 22, which works out to be 303,600 different slates of officers possible. Now, if you look back at it, where do these numbers come from? Well, the first number is the number of people you're choosing from, 25. And then we just go down 1 each, where the total number of factors here is the number of offices or number of people that we're choosing. Now, I want to think back to the factorial function that we had before, and you may look at this, and in one sense we're making this a little bit harder or more complicated, but in another sense not. So I'm going to take this 25 times 24 times 23 times 22, which is really the best way to think of it in a way, but I could multiply top and bottom by 21 factorial if I wanted to. Okay, well, then you can express the numerator as a factorial, 25 times 24 times 23 times 22, and then this part here is 21 times 20 times 19 times 18 all the way down to 1. So the whole numerator becomes 25 factorial. The denominator is 21 factorial. We could think of 21 as 25 minus 4. So then how does this come to be come from our original numbers? The numerator is just n factorial, and we're dividing by n minus k factorial, which is the 25 minus 4 factorial. That's the 21 factorial here. The k being the number of offices or number of people that we're choosing. So a lot of times you'll see it written this way, and this way up here maybe is a little more useful, but they're both correct. So summarizing, we're counting choices where the order matters and repeats are allowed. So we're choosing from a set of n distinct objects. We choose an ordered list of k of these objects. Notice that n is a natural number and k is a natural number less than or equal to n. Repeats are not allowed, so this is called without replacement is another way to say that. Because it's like as if you were drawing a name from a hat for the first one. Do not put it in when you draw the second one, so it can't be repeated. So that's why it's called without replacement. Okay, and we have a shorthand notation for that. It's called NPK. It's called a permutation. We read that n permute k. One way to write it with factorials is n factorial over n minus k factorial. We can also write it in product notation as the product from I equals 0 to k minus 1 of n minus I. So what this last thing means, this part right here, means you plug in 0, so that just gives you n minus 0 as n. You plug in 1, that gives you n minus 1. You plug in n as 2, and it works down. The last one is n minus, parentheses, k minus 1. So if you look, that's a total of k factors. So just like the one we were doing before here, this was 25 permute. This is 25 permute 4. So there are 4 factors starting with 25, working our way down by ones. 25, 24, 23, 22, for a total of k equals 4 factors starting with n equals 25. And that's what this is, just a shorthand notation for the product of a bunch of things. And we have an even shorter notation for it, and that's, we actually have 3 versions here that we might use. It's NPK, or n, where these are both subscripts, okay? And so the n in all these versions here, n is how many you're choosing from, k is how many you're choosing. You can also sometimes see it this way, NPK with n is the superscript, k is the subscript. I don't see that one as much, but you often see it this way, p of nk. I have seen it, actually I think that I've actually seen it this way, it's NPK of n and k as well. So a couple of different versions, and we'll see a little bit more about this in a minute. So let's see if you can do some computations with these things now that you've seen these. So see if you can, without a calculator, let's see if you can do this without a calculator. Compute 7 permute 3, and then compute 27 permute 4, and then for any n, compute n permute n permute 0, n permute 1, and n permute 2. So those last 4 could potentially be functions of n. Okay, press pause and work this out. All right, let's look at the answers here. So we can think of it, 2 different ways to think of it. We can think of it as 7 factorial over 7 minus 3 factorial. That's 7 factorial over 4 factorial. So then we think of the 7 factorial as 7 times 6 times 5 times 4 factorial. The 4 factorials cancel, and we get 7 times 6 times 5. It might be easier just to start with the 7 times 6 times 5. The way you do that is you think of the 7 first, then you just work your way down 1 until you get a total of 3 factors. 7, 6, 5, that's 3 factors. Anyway, then you end up multiplying those together. Let's see, 6 times 5 is 30, times 7 is 210. Similarly, we can do 27 permute 4. You can do it 2 ways again. You can think of it as 27 factorial over 27 minus 4 factorial. 27 minus 4 is 23 factorial. It's a typo. Let me fix that. Okay, that's better. Now it's a 23, but the rest of it was right already. So the 23 factorials cancel, and you're left with 27 times 26 times 25 times 24. So if you like the factorial version of the definition, you'd have to do it that way. If you like the product definition, which is equivalent, you could go straight to here. I kind of like that better. Just start with 27, and then you multiply by 26, 25, 24, go down 1 until you have a total of 4 factors. 1, 2, 3, 4. Now you just multiply these out by hand or with a calculator. If we're doing it completely without a calculator, you'd have to do it by hand. And but it's just multiplication. So we could do this. It might take us a minute, but we could do it. 421,200. Or if we do it with the calculator that just does multiplication, basic 4-function calculator, we could do it there. Now the next one is n permute n. Well, by definition, that's n factorial over n minus n factorial. That's n factorial over 0 factorial. 0 factorial by definition is 1, so this is just n factorial. Again, what do? We do n times n minus 1 times n minus 2, all the way down for a total of n factors, which would go all the way down to 1, which is what the factorial does. So n permute n is just another way of saying n factorial. N permute 0 is n factorial over n minus 0 factorial. That's n factorial over n factorial, which is 1. So if it doesn't matter what the first number is, if you're choosing 0 from it, there's only one way to do that. You don't choose anybody. So that makes sense. N permute 1 is n factorial over n minus 1 factorial. N factorial is n times n minus 1 factorial. The n minus 1 factorials cancel, leaving just n. So if you take n and just permute 1, you always get n. If you take n, excuse me, n permute 2, that's n factorial over n minus 2 factorial. So it's n times n minus 1 times n minus 2 factorial, which cancels with the denominator, and so you get n times n minus 1. Now, luckily, these functions, just like the factorial, these are built into the calculators. So on a TI-84 calculator, it's pretty easy to do it. The format's just slightly different on the two calculators. So the way this works on the 84, it basically uses the NPR, this version here, of the permutation notation. And you put the n value first, and then the r value second. So if you want to do 7 permute 3, you put 7 NPR 3. Now, of course, 7 and 3 are just basic keys on the main screen, right on the keyboard. But NPR, you have to go to a menu. And the menu you go to is Math, Probability, number 2. So you hit Math, and it comes up with this menu here, and the cursor will be over here, and these will look a little different. You can either do right arrow twice or the easier left arrow once to get to Probability. And you'll see right there's the factorial where we found before. Okay, and then the NPR is right there as number 2. So I just type number 2 or move the cursor down on that and hit enter. That'll give me the NPR. Then I finish up by typing the 3 and enter, and you get 210. Okay, now the TI Inspire calculator is very similar. First of all, you're in a calculator screen, calculator home screen. Press menu, and then this menu comes up here. Go down to number 5, probability, or just hit 5. And we're going to choose permutations, which is number 2. So if you want, you could just, if you know the numbers, you could just press menu 5, 2, or do that as you go, or you can use your arrow keys to move around. That gives you the NPR open parentheses, and you have to put in the N and the R in order with a comma between and close parentheses. So for example, 27 permute 4 would be NPR of 27, 4, close parentheses, hit enter, and you get 421,200. So then the next thing I would suggest doing is maybe, at least these first two, maybe try these on your calculator and make sure you can get the same answers out. I'll put it back there. You can pause if you want. So get your calculators out and try this, and then press pause when you're, press play when you're ready to go on. Okay, did you get those to check out? I hope so. All right, here's some more practice. So these, let's look at the calculator and have it do the calculations for us. So use your calculator and compute these 4 different permutations. 37 permute 15, 18 permute 10, 52 permute 5, and 33 permute 7. Just do this using your calculator. Go ahead and work it out. Come back when you're finished. Press pause now. Okay, and so we have these answers here. It is interesting to note that the Inspire, especially the CAS version, will give you all the digits even if it gets really big. And it will do it in standard notation, whereas the TI-84, which is the screen at the top, will go into scientific notation if it gets very big. So, for example, the last one, 33 permute 7, it actually is going into scientific notation here, but we actually should know that well, we may or may not know it, but the next one is the last digit is 0 there. So that, what is that? 21,531,121,920. Working our way back up from the bottom, 52 permute 5 is it's actually 311,875,200. Both calculators gave that one exactly. 18 permute 10 is actually 158,789,030,400, which the Inspire gives you basically just like that, except for maybe the commas. But where the TI-84 goes into scientific notation. And here's the exact value down here in this screen for the 37 permute 15. Actually, it ends in a, let's see, well, I rounded it off to the same number of places as the TI-84 would do and gave it in scientific notation, approximately at least 1.02245,324 times 10 to the 22nd power. In fact, let's see, 12245,324, and then after that the digits should be 002983751680000. It should be the exact value. So use your calculator to compute the following: 70 factorial over 65 factorial. Well, you run into a problem if you just try to type it in like that, at least on the TI-84, because 70 factorial is bigger than 10 to the 100th power, and so that's too big for the calculator to work. But we could do it without that, because if you notice, 70 factorial is 70 times 69 times 68 times 67 times 66 times 65 factorial, and that's over 65 factorial, so I'm just grouping the 1 to 65 factors in the 70 factorial together, writing out each of them individually for the 66 up to 70. The 65 factorials cancel, and you're left with 70 times 69 times 68 times 67 times 66, which of course we could do, as you see here on the calculator, and get 1,452,361,680. But if you realize that this is a permutation, that's an even easier to do. You notice that 70 factorial over 65 factorial is really just 70 permute 5. And so you can do that 70 MPR 5 on a TI-84 and get the exact answer there. Okay, so here's an application. See if you can work this out. You can use your calculator here. Suppose that there's an organization with 57 members and they want to select a slate of 8 distinct officers. No individual will be chosen. Every office is held by a single individual, and every single individual can hold at most one office, so no repeats. How many slates of officers are possible? Press pause, work this out with your calculator, and come back when you got an answer. Press pause now. Well, hopefully you realize that this is exactly the situation we've been studying in this video. So this turns out to be 57 permute, well, it's NPK, so 57 permute 8. So you could just do that on the calculator. You see it worked out both here on a TI-84 and a TI Inspire. And it's at least approximately 6.66 times 10 to the 13th power. Actually, by looking at the Inspire, you see that it's exactly, let's see, what is that? 66,625,230,670,000. So let's just review real fast before we go on. So we use this counting technique when we're counting choices where the order matters, repeats are allowed. We're choosing from a set of n distinct objects. We choose an ordered list of k objects. So starting with n objects, choose k of them where what? Repeats are not allowed. Okay, and so the choice of offices is, our choice of the number of choices is n permute k, which we can do on our calculator. That's called a permutation. Notice that order matters and repeats are allowed. Repeats are not allowed, that should say. Let's fix that slide. Okay, there we go. I had it correct down here. Without replacement, repeats are not allowed, but I didn't have it right in the heading, and now it is correct. Let's end with that for this video.